Welcome to 1007 ICT, 1807 ICT, and 7611 ICT, Computer Systems and Networks. This is Lecture 3C, Digital Logic and Digital Circuits. So last time we covered the logic unit, selection logic, decoder logic, and we put some of those together, particularly the selection logic and the decoder logic. We ended up with something called a multiplexer. So a multiplexer allows us to take multiple inputs and lets us choose one of those inputs as our output. It's like a big dial, you just select the one that you want, and there's some mechanisms for doing that. We also looked at demultiplexing, and finally we looked at half adders and full adders. And once we've got those circuits, we could do addition and also subtraction based on our 2's complement negative numbers. So in this lecture, we're going to look at something called an arithmetic logic unit, or the ALU. We're going to look at binary multiplication and division, shifting, then finally in the red section there we're going to look at sequential logic, which is a little bit different to what we've looked at so far, and in particular we're going to look at data latches, something called an SR latch, clocks and synchronization, and eventually we're going to use this to build some kind of memory. And a memory, you need to be able to remember what's happened previously. With the circuits that we've seen so far, we can't remember anything. If you get 2 inputs coming in, the circuit will analyze it, work out what the process is. Like if it's an AND gate, it'll perform the AND operation, and you'll get an output. If you change the inputs, immediately that processing will happen and the output will change. There is no way to remember any kind of data. So the learning objectives, we are going to learn or gain an understanding of all those things I just mentioned, the ALU, multiplication, division, shifting, sequential logic, and eventually how we build a basic memory. Looking at the arithmetic logic unit. So an ALU, or an arithmetic logic unit, is a general processing element. It puts everything that we've seen so far together in one place, and we can combine these ALUs in parallel to make multiple bit versions. So a single ALU works on a single bit. If you have a 64-bit computer, how many of these ALUs would you need? Yes, 64, great. Okay, so one for every bit that you need. So you can just glue them together, and I'll just talk a little bit about the ALU, how it looks, in terms of just the diagram. You remember this shape that we have here, right? This one? This was our multiplexer, so we've seen that one before. It takes in multiple inputs, in this case 4. You select which one using the selection lines. In this case we have 4 inputs, we need 2 selection lines. If we had 8 inputs, we would need 2 to the 3 or 3 selection lines. If we had 16 operations or inputs, we would need 2 to the 4, which is 16 inputs. Does that make sense? Okay, so we have some inputs on the left, we have some way to select which input, and the actual inputs are coming from a variety of different gates. In this case, we've got AND or XOR. In lecture 3B, I think we had a NOT gate here. In this particular ALU, we've got a full adder, so this one can do maths. Okay, can we put other operations in there if we like? Sure, right? All different machines will have different capabilities. This one has these 4. Different machine might have slightly different ones. Just as an addendum to that, the full adder has a carry in coming in and a carry out as well, in addition to A and B coming in, because it's doing some maths and you have the carry and so on coming in and out of that mathematical operation. What I'll do next is I'll show you just how that relates to the diagram on the right. So this shape, it's like a big V shape, is one of these. Does that make sense? So if you take this thing and you kind of rotate it, you've got one of these. How many are there on the right? 1, 2, 3. This is a 3-bit ALU. If you had a 64-bit machine, you would have 64 of them next to each other. Okay, so you can just glue them together. So once you've got one of these, you can just copy it and paste it in some sense. Okay, and you can build a more powerful machine. Now, what does that mean? Well, if I have a 3-bit ALU, imagine if I have this 1, 1, 0, and I want, this is my A, and I want a B here, 0, 1, 0. Supposing that I want to do one of these operations, I don't know, let's pick AND, the first one. If I AND these 2 things together, what do I end up with? 0 and 0 is? 1 and 1 is? 1 and 0 is? 0. And, yep. Okay, how does that map to these things? Well, A is 1, 1, 0, and B is 0, 1, 0. You can see how they map together. So the A input for the first ALU is A0, and the B input for the first ALU is B0. That happens to be this column. So the answer to this output, or the output here, would be a 0 if we're doing AND. Does that kind of make sense too? So they're working in combining some of our inputs like this. So we could have multiple inputs on the top, we have multiple outputs on the bottom, and we can do computations. So that's an ALU. We can glue them together to get multi-bit versions, and it can do the processing for us. Moving on to multiplication and division. So we found that addition was pretty easy, right? Just the basic addition was okay. Then when we tried to do subtraction, we found it was more difficult because we had to deal with negative numbers. So we used something called 2's complement. Again, it wasn't particularly difficult, but there were a number of extra steps that we have to take because we have to convert to negative numbers, right? So we saw in the previous lecture, we saw an addition unit. We saw the logic for it, right? A full adder. And then we saw how we can adjust it to do the subtraction as well. That was on the previous set of slides. Multiplication is similar in a sense. The basic multiplication and division is very simple. The machine is very good at doing this. So multiplying and dividing by 2 is really easy. Multiplying and dividing by other numbers is not as easy. It's not as straightforward. So we have to do a bit of work to make that happen. So we'll have a look at multiplying by 2 and dividing by 2 first, and we'll see why that's actually not too difficult. So looking at multiplication by 2, let's pick a number. So 1010. This is a nice even sort of number. 1, 2, 4, 8. What number is this? 10. Right? So it's a nice number for us to work with in base 10. So 10. Imagine that I do this. So I take this column here. What's the next column? The 16's column, right? So I take this column and I shift this one over here. And then I take the 4 and I shift it there. And the 2 there. And the 1 column there. Is there a gap here? Yes. I need to fill that gap, so I'm going to push in a 0. I need to put something in that column. It's going to be a 0 in this case. And so what's my new value? 16 plus 4 is 20. What happened to my number? Multiply by 2. Can you see why? Because every column to the left is double the one to its right. So if I move everything one column to the left, I have doubled every single column. Right? So whatever the number was, it's now double what it used to be. If I did this again, what's the next column? The 32's column. So this is now in the 32's column. That 0 is in the 16's column. That 4 is in the 8's column. This 2 is in the 4's column. This 1 is in the 2's column. And again, I've got a gap here, so I need to put in a 0. And what answer is this? 32 plus 8 is 40. So every time I shift left, in this case, what's going to happen to my number? It doubles. So can you see that multiplying by 2 is really easy? Yeah, it's an artifact of having these binary numbers with those columns, and they double every time that you go to the left. Okay, I can do that fairly easily for multiplication. What about division? What do you think? Shift to the right. Okay, so let's start with this number. So 1, 2, 4, 8, 16. What number is this? 20. And let's shift to the right. So the 16 goes into the 8's column, the 8 goes into the 4's column, the 4 goes into the 2's column, and the 2 goes into the 0, so the 1's column. Where does this one go? It falls off the end. We just destroy it. And what's my answer now? 8 plus 2 is 10. Dividing by 2 is also really easy. What about if we do it again? I get 5. Okay, and this one is a little more interesting. What if I do it again? I get... that 1 falls off. This is a 2. So 5 divided by 2, is it 2? Not in our normal maths, but we're using integer maths. We have no way to work with fractional parts. So it will just chop off the fractional part. And if you chop off the fractional part of 2.5, what do you get? 2. Okay, so it does make sense. It's an artifact, again, of the number system that we're working with. So again, division and multiplication by 2 is really easy. The machine is actually quite good at doing this. Do you think there is some hardware that lets us do this quickly? What do you think? Probably, right? So we have some hardware called a shifter, which does exactly that. If you shift left or right, The outcome, if you shift left, will be that you double the number. If you shift right, the outcome will be that you halve the number. Down the bottom, you'll see there is a diagram there of those yellow shapes again. What was that yellow shape? It was a multiplexer. It takes in multiple inputs and gives us one output. How many inputs does each of those multiplexer boxes have? Let me go to the diagram and I'll point out which ones I'm talking about. So this box, how many inputs does it have at the top? 2. I have 2 possible values to choose from. That means I can use a single bit to select. My previous ones had 4 possible inputs to choose from. I used 2 lines to select. Okay, so each of these, you'll notice that this line here goes into every single one of them at the same time. So are we always choosing the same value or the same input for each multiplexer if we're using the multiplexer? Yes, they're happening at the same time. It's choosing the same side. How many sides do we have? Left and right. So we've got 2 sides. Let's have a look at a number. 1011. This is the number we start with. We're going to shift it. So let's say that we shift, I don't know, this way. Which way am I shifting? Right. Okay. So I'm going to follow the lines, shift right. So a 1 comes out here, a 0 comes out here, and a 1 comes out here. Where does this one go? Can it go to the right? Nope. So it's just lost. Does that also make sense? What about this one? Does it have a value? Not at the moment, but we can put a 0 through here, and now we have a leading 0. Is it still the same number? Yes. You'll notice also here it says sign. If I'm working with a plus or minus number, I need to keep the sign bit. If it's a negative number, it's a 1. Do I need to keep that? Probably, right? Because I don't want to change from a negative to a positive just by shifting. Okay, so this is a complication. We don't really need to worry about it for now, but we need to know that potentially you do have to deal with plus and minus numbers. Okay, this thing here is saying left or right. What do you think that's doing? It's saying choose which side to work with. Which side you let through, which side you stop. Okay, so that was shift right. Do you think shift left works the same way? Same process, just you choose the other side. So this one, can I shift left? No. Okay. What about this one? Yes, so the 0 comes out here. This one? The 1 comes out here. This one? The 1 comes out here, and now we shift in a 0 on the end. What have we done to our number? We shifted it to the left. If we were thinking about multiplication, we have multiplied it by 2, except this guy was lost, right? We don't have the space for it. Does that also make sense? Do you remember we have limitations in how many bits we have? Okay, so that could be an artifact of how we've done this particular operation. Question? Okay, there's a question about the sign bit. Okay, so the sign bit, we need to keep track of it. So yes, there are issues that we have to deal with the sign bit. That one was only showing you 4. Right? Typically, we'll have bigger values for the sign numbers. But yes, it's definitely an issue, and you can do the wrong thing. Does that make sense? Yep. And so one of the ways you might address that in some sense is you might have one operation that shifts left for signed numbers that does it a particular way, and another one for unsigned numbers that does it a particular different way. That's a potential solution. Okay, so that's a shifter. Here is a more complicated shifter. It's the same thing, but there are just more inputs. How many inputs are there for each multiplexer? 4. If I have 4 inputs for my multiplexer, how many selection lines do I need? 2. There they are. And what are my combinations here? I've got 0, 0, 0, 1, 1, 0, and 1, 1. Those are the possible values for those selection lines. The output is determined by which one you choose. So if you choose or select 0, 0, you are going to get 0 on the output. This is useful for when you get a value coming in and you want to initialize it to 0. You don't care what it was, you just reset it to 0. Okay, that's why you might use that one. 01 is shift to the right. We just saw that one. 10 is shift to the left. We saw that one as well. And 11 is let whatever is there go through. So let's just have a look at the different values here. We'll use the same number just to keep it consistent. So if I'm putting zeros through, so if I select 0, 0 here, which one am I choosing? This one? Yeah, that fourth one. And what's coming into that fourth one? Just the value 0. So what am I going to get out? Zeros. We don't care what the input was. We just give you 0. Is that useful sometimes? Yeah, if you want to reset something, you don't actually care about the value that came in. You just want to clear it. You can do that. So this one is more powerful than the previous one. It allows you to do more things. Okay, if I use this one, this is the right shift. So basically I would do this, it'd go through the right one, okay, and then something would come in here. Does that make sense? Yep, so it's just a shift to the right. That's the same as the previous one. What about shift to the left? This one can't go anywhere. This one goes here, this one goes here, this one goes here, and we get a 0 coming in. Same as the previous one. Okay, so that part is not different. The one that is different is through. And through may be a little bit difficult to think about, but what you want sometimes is, look, this box here, this box is in the way of my number. Yeah, my number has to go through it. Now sometimes I don't want to do anything to it. Sometimes I want to shift left, sometimes right, sometimes I want to set it to 0, sometimes I want to do nothing. So I need some way to just let the number go straight through. So which one is this? 1, 1 will be this one, the T line, and what happens with the T line? It's this. Straight down, straight through. So you end up with 1, 0, 1, 1. Can you see, depending on the purpose you have in mind, you will use this thing in different ways. You can multiply, you can divide if you think of them in that way. You can let the number through, you can set it to 0. So it's a more generally useful shifter than the one I showed you on the previous page. The other one you could just shift left and right. So you had to change the number. So now we move on to arbitrary multiplication. So I mentioned that just multiplying by 2 is not difficult, just because of the way the system works. But multiplying by something like 5 or 11 or 97 is much more difficult, because it's not so easy to work with those columns in the same way. So we're going to do a little trick, right? We're going to break our multiplication up into smaller steps. Okay? And so there's a couple of ways we could do that. So the first way is, if I have a number like a times b, so 3 times 5, okay, I could work it out as 3 times 5 is 3 plus 3 plus 3 plus 3 plus 3. Does that make sense? Yep. So we could definitely do that. Is that fast or slow? It's slow. It's multiple additions, yep, and I may be able to do it faster. So what we can do instead is we can use the shifter to help us. So we're still going to multiply by 2 in some sense, but we're going to set it up so that we're multiplying by the correct powers of 2. So here is an example. There's a couple of examples here. I'm just going to draw this rather than talk to that example, because I think it will be clearer if we do that. So this is the same example, by the way, but 10 times 5. So what's 10 times 5? 50, right? Okay. So it's a nice and easy number to work with. Is this the same as 10 times 4 plus 10 times 1? Yes, that would be 40. That would be 10. The answer would be 50. It's also the same as a lot of other multipliers if you wanted to work that out. Now I chose 4 and 1 here for a reason. 1, 2, 4, 8, 16. Are 1 and 4 in this sequence? Yes. With binary numbers, here's a more general question. Have we been able to represent any value just using these binary number columns? If I want to represent the number 53, can I do that with my binary columns? Yes. What about 78? 11. Any number you can think of that's a whole number we can represent. So we can set it up that we can split this number here, the second number, into powers of 2. Would you agree with that? Yes. And that's what we're going to do, because each of these powers of 2 is a multiplier by some number of 2's. Okay? If I multiply something by 1, how many 2's am I multiplying by? No 2's. If I'm multiplying something by 4, how many 2's am I multiplying by? 2 2's. Does that make sense? Sort of? Yeah? We'll have a look at an example. So, if I were to do 10 times 5, right? Okay, so let's see if I've got 10. 1, 2, 4, 8. 10 is an 8 plus a 2. Is that correct? This is our starting number. What we're saying is we are going to use this shifting to multiply it first by 4. If I multiply it by 4, how many times do I have to shift it? The first time I shift is multiplying by 2. The second time will be multiplying by 4. So I'll shift it twice. If I shift this number twice, this is 10. If I shift this twice, all right, what will happen is I'll have 2 zeros on the end here and then. Sorry. 2 zeros here. Does that make sense? So this 1 has moved 2, that 0 has moved 2. Yep. Okay. So basically all I've done is I've added 2 zeros to the end of it. That's another way to look at it. What number is this? This is a 16, this is a 32. 32 plus 8 is 40. So is this 10 times 4 by shifting it twice? Yeah, sure. Okay. What about 10 times 1? Well, 10 is this. If I multiply it by 1, does it shift or change? No, so it just stays as 10. I shift it, but I shift it 0 times. In terms of my shifter, I could just use it through. Does that also make sense? We saw the through operation before. You could just let it go through. Doesn't change anything. Okay, so 40 plus 10 is, well, 101000 plus 1010 is this. And this should be 50. 32 plus 16 plus 2. Yeah, that will give me 50. So the way we're going to do multiplication is we split the second number up into the powers of 2 that it has, in this case 1 and 4, and we use those powers of 2 to work out how many times we shift it, and then we add up our shifts. That's the process. It's involved, but the basic process is the same as multiplying by 2. Okay. Here is a slide. I'll get you to read this one in your own time. I'm going to show you an example that illustrates how this works, but you can refer back to this one as a slightly different example. This one is 10 times 13. Okay, I'm going to show you 9 times 13, so you can relate it to that example. So before we start, what's useful at this point is to work out, if I'm going to multiply 9 times 13, what is it going to look like? Because I'm going to do a lot of steps, and I want to make sure that I get the right outcome, and I can tell that it's the right outcome. So 9 is 1001. Is that correct? An 8 plus a 1? What about 13? An 8 plus a 4 is 12, plus a 1 is 13. Great. And the answer apparently is 117. So 9, 10s, 90, 117 seems all right. Yep. So now I've got my answer here. Let's work out what the answer is just using decimal. So 117. 117. Is there 128 in 117? No. So there is a 64. So there's a 64, and what's left? 53? Yep. So there's 53 left. Is there a 32 in 53? Yes. And what do we have left? 21? Okay. Is there a 16 in 21? Yes. So we subtract 16. We've got 5 left, so there's no 8, but there is a 4. And there's 1 left, so there's no 2 and 1, and we end up with a 0. So this is my answer. This is 117. Now, I didn't use the binary multiplication to do this. I used the decimal, right, and I worked out the values. And I'm doing this so that when we do the actual binary multiplication in a second, we can check it. We can see, yes, actually, this is the right answer. So that's the answer, 1110101. So here is the full work example, and you can also refer back to the lecture slides, which has the 10 times 13 example. It shows the same thing, just for a slightly different one, and hopefully between the two you can just work out, okay, that's what's going on. So we've got here this number. What number is this on the left here? That one. 9, and it's 13 over here. So 9 times 13 was 117, correct? That's what we worked out. Okay. Let's have a look at how we generate this. I've partially filled this out. So we start with 1001. This is our number, 9. Okay? And what we're going to do is we're going to shift it 0 times, we're going to shift it 1 time, we're going to shift it twice, and 3 times. Why are we only going to shift it up to 3 times? Because this is 2 to the 3. That's the biggest digit we have. Yep. We do not have a 2 to the 4 in my multiplier. So we won't be working with 4 shifts. I've left a gap here, and this gap we're going to use for what value is in here, because sometimes we do this if there's a 1, and we don't do it if there's a 0. You multiply anything by 0, you're going to get 0. Okay, so let's go through it. We have 1001 shifted left 0 times. So this is the 2 to the 0 column. That's where the 0 comes from, this 0. And how many times do I do it? Once. So if I shift 1001 0 times, what do I end up with? 1001. It doesn't change. Yep. I multiplied it by 1 is what I've done. Okay. What's 2 to the 0, by the way? 1. So I'm multiplying it by 1, okay, because there's a 1 in that column. What about the next column? Well, 1001 is my number. Shifted left once. This is the 2 to the 1 column. What's in this column? 0. 0 times, so 0 times anything is 0. So we might have done the shift, but the answer is going to be 0. What about the next one? 1001 shifted left twice. That's the 2 to the 2 column. How many times? Once. You shift something left twice, you get 2 zeros on the end, and then 1001. It's a bigger number. It's shifted left twice. What's actually happened to it? It's been multiplied by 2 and then by 2. 4 times. So multiplied by 4. And the last one, 1001 shifted left 3 times. This is the 2 to the 3 column. What's in there? There's a 1. 3 times will be 3 zeros, and then 1001 just to the left of that. Are we finished? Well, not yet, because this is an addition. So let's do the addition. 1001 plus, and this one. So I'm adding these two together. I don't need to add the 0 because it's 0, obviously. So what do I get? 101101. This sum is not yet complete. I have another term to add to it, and that number is this one. 1010, carry the 1, 1, 1, 1. Does this number look familiar to you? 111001. What was the answer from the previous slide? 111001. So did this process correctly calculate 9 times 13? What do you think? Yes. It may take a little bit of time to get used to that process. What you're doing is you're using the powers of 2 to work out how many times to shift, and then you're using whatever's in that column to work out what you multiply that thing by, right? So how many times you're doing that. That is arbitrary multiplication. It's a little bit more complicated than the basic multiplication, which is multiplying by 2, but it uses that same process. You're just multiplying by 2 just a certain number of times, and then you're adding those terms together. When we do arbitrary division, we can use basic binary long division. So if you remember, maybe a while back, you did long division probably somewhere. Yeah, I'll show you how it looks, but basically it's with binary numbers. It works exactly the same way as the decimal base 10 long division, and it has an answer and a remainder. So we'll do the same thing. I've got a number 26 divided by 4. Apparently that's 6 and a remainder of 2. So 6 fours are 24, and there is 2 left over. That makes sense. Okay, so 26 is a 16, an 8. What are we up to? 24? No 4 and a 1 and a 0. That's 26. What about 6? 6 is 1, 1, 0, a 4 and a 2. And the answer is, sorry, the answer should be divided by 4. There we go. And the answer is 6 divided, and if you divide that, you end up with a remainder of 2. So 26 here divided by 4 is 6 remainder 2. Okay. Now I've done that again in decimal sort of to work out what my answer is going to look like, because I'm going to have a lot of 1s and 0s on the page. It's useful for me to check, am I getting the right result? Am I even getting close to the right result if I'm doing the working? So long division, how does it work? Well, we've got 1, 1, 0, 1, 0 here, and then we've got 1, 0, 0 on the left here. A lot of 1s and 0s. This is a 4, this is a 26. It's natural to try and read this as this thing divided by 100. Try not to do that because it's base 2. You will misinterpret what it means if you do that. So first thing, does this 100, and I'm going to call it 4, does 4 fit into 1? No. Does it fit into 1, 1? What's 1, 1? 3? 4 into 3? No. What about 110? This is 6. Does it fit into 6? Yes. How many times? Once. So I'll put a number 1 up here because it divided once. I subtract 4 from 6. What do I end up with? 2. 2 is 1, 0. You notice we're working in binary, right? So can I ever get this thing going into this more than once? No, it'll be either a 0 or a 1. So that makes it a little bit easier. I've got 1, 0 left over. Does 100 fit into 1, 0? 4 fit into 2? No. I grab the next column, and now I've got 101. Does 100 fit into 101? Yes. How many times? Once. What's left over? 1. Does 100 fit into 1? No. So I grab the next column, 1, 0. I've got nothing left here, so does it fit into 1, 0? No. So it went 0 times, right? And my answer is 1, 1, 0. And my remainder is 1, 0. So the process gives you the right answer. And it's exactly the same as the decimal long division. So if you know that already, you can work through that fairly easily. It is a little more confusing, right, because there's so many 1s and 0s on the page, but the principle is the same. So now we've seen how to do arbitrary multiplication using shifts, and now arbitrary division using these long division. The next section that we look at is sequential logic. So previously we looked at combinatorial logic, and basically that takes some inputs, does some processing, gives you an output immediately. If you change the inputs, the output changes immediately. If we want to build something like a memory, we need to make some changes to that. And the basic thing that we want to do is have something that relies not only on the current inputs, but also on the history, what happened before. So the diagram down the bottom there, we'll have an input, goes into a logic function, whatever that is. There's some kind of memory cell that remembers what happened last time, and that memory cell is fed back into my logic function. So we can get some kind of remembering of what happened before. The idea that we're talking about here is called a data latch. And we need this thing because previously our functions just let things in and gave us an output straight away. We didn't have the chance to capture it. So a latch is a logic function that can store bits. There's an example here. So this is the first example. I'm just going to draw this one so we can have a look at it. This one is pretty basic, and it actually doesn't quite work, but it gives you an illustration of what we're trying to achieve. So here's an OR gate. Imagine that when I start my system up, I've got a 0 coming in here and a 0 there. So the initial state is 0. There's no power. So 0 or 0 is 0. In these diagrams, you'll see Q is usually the answer, and you might even see a not Q, which is the opposite of the answer. You might get both on some circuits. Okay, so 0 or 0 is 0. So we've seen that before. If I change my input up the top here to be a 1, 1 or 0 is 1, and that means that this now becomes a 1. 1 or 1 is still 1. Great. And it stays like this. It remembers what happened before, right? If the inputs stay the same. What if I change my 0 or 1 is 1? Can I change it ever back to a 0 again now? What do you think? No, I've locked it. So this is not a complete memory, but it can remember a 1 once. It's kind of like the old CDs where you could burn them once, and once you burnt them, they were stuck, right? These days, that technology can write them multiple times, but that's a similar kind of idea. So is this particularly useful to us as a memory? No, the idea is okay, but it's not complete. So we need to do something a little bit more, little bit better than this. And so what we actually need to do is we need two inputs. We need one to give it a 1 and one to give it a 0. So we need two ways to tell it information. And that's the one down the bottom. Now I'm going to move over to Logisim here because it's going to be much easier to describe this using Logisim. So here's the circuit. That's the one at the bottom of that page. It has two inputs, a set and a reset. Set means put a 1 in. Reset means reset it to a 0. At the moment, you'll see there's some red in my circuit. So red's a bad color. What it actually means in terms of the simulation, at the moment, the simulation can't work out what the original value is. It's not like in the real world where you have power or you don't. It doesn't know. So I might need to tell it what the initial value is. So when I touch one of these the first time, it will work out what it should be, right? So typically seeing red is a bad thing. In this case, it's expected because it doesn't understand what the starting value will be. So we said that set is put a 1 in. So there's an output here. And if I put a 1 in, what do you think that output will change to? It should be a 1. Okay, so I do that, and the output is 1. Now, if I turn this one off, does it still remember the 1? Yeah, it does. So it's a memory. If I want to reset it, I should click the bottom one, and it should go to a 0, and it does. And I can click this as many times as I want, and it will still remember the 0. It will only change when I click the 1 again, and so on. So there's a couple of states you've seen. The first one is if I give it a 1 with the set, it stores a 1. If I give it a 1 with the reset, it stores a 0. Right? That's the 1, 0 and the 0, 1 states. There's also, at the moment, the 0, 0 state. Can you see that one? Is anything changing in my circuit? So it's stable. We call that the stable state. A bad state is this one. I'm setting and resetting it at the same time, and actually I'm not really sure what the outcome will be. It depends on the timing, what the outcome will be. So you should never have a 1, 1 state for these systems. That all also makes sense? Right? Because you're getting conflicting inputs. So that's a basic data latch, a basic memory. You saw that it could remember the 1s or the 0s. We can rearrange these a little bit, and we will do that, but you might do that for different purposes. So this one, you'll see it goes through a sequence of iterations using an AND gate with a NOR gate, then 2 NOR gates. And the bottom one on the right there, you'll see that there's this kind of a feedback loop happening where the top one feeds into the input of the bottom one, and the bottom one feeds back into the input of the top one. Can you see that? So there's a feedback loop going on. Do you think that feedback loop is instantaneous? It can't be, right? It'll take a certain amount of time. That actually causes a problem for us. I just want to show you that this is that diagram, and it works exactly the same way. Again, it's red at the moment. It doesn't know what the input state is. If I give it a 1, well, Q at the moment for this one is down the bottom, so that's the answer, and you'll see a not Q here as well. So at the same time, you've got the answer and the opposite of the answer. So if you need either of those, you can just pick them up really quickly. You don't have to recompute. What about if I want to set a 0? You see the output now is 0, and the opposite is a 1. And I can, again, it's a memory, it remembers. I can set a 1. I don't want to set them both to 1 at the same time because I can get inconsistent states. The thing that I was talking about before was this little bit in the middle here. There's a feedback loop. That feedback loop is not instantaneous, which means that there are some periods of time when my circuit is not stable. I can't use the output properly because it hasn't quite resolved itself yet. Okay, so that's a problem, and we need to deal with it. So that's what the next one deals with. You need some kind of synchronization, something that says, now I can use it, now I can't, or I shouldn't. Now I can, now I can't. And we call that a clock in this environment, and basically it's a thing that just goes from 0 to 1, 0 to 1. Yes, I can, no, I can't. Yes, I can, no, I can't. Or at least that's how we're using it. So the main problem with latches is that after the inputs change, the output is unstable for a short time. If you try and use it during that time, it won't work properly. And a clock signal can control when we can access it. You see a diagram there. I'll show you this one as a drawing, a Logisim drawing. Same thing. The difference, or at least this part is the same. That part. That hasn't changed. The difference is there are now 2 AND gates. There is my set and my reset, and there's a clock here. If you remember back to the previous lecture, when we have a series of AND gates in a sequence like this, how are we using them? They were blocking things. Do you remember that from the other diagrams? So we're actually blocking stuff from happening by using those AND gates. So if you notice, I click 1 here, nothing happens. That AND gate needs another input to be set to 1 for that signal to go through. Okay, at the moment, that input is 0. Why is it 0? Because the clock at the moment is 0. If the clock is 1, you notice both these AND gates are now active. If I do this, my circuit changes. I can do this as many times as I want, but the circuit remembers what I just did. Then the clock goes low, for example. I may try and change it again. It won't change until the clock goes high, and then I can change it. So what's the clock doing for me? It's a switch. It's allowing me to access the circuit or not. Yep, it's switching it on or off, actually, in some sense. And so those AND gates are blocking the signal, and the clock is saying, oh, you can go now or you can't go, right? And so you restrict access to the right-hand side of the circuit only when you believe that that part of the circuit is ready for a value to be used. So the timing is important here. And those things are sometimes called flip-flops. And the faster the clock, the faster that you can be reading or writing the data into that data latch. So the clock speed is important. If you make the clock speed go too fast, right, then you run the risk of not having the data ready, right, by the time that you're trying to read and write it. Okay. We move on to the final version of this data latch, which is a D latch or a D flip-flop. And the only difference that you'll notice, well, two differences, they're all NAND gates. We saw before that sometimes we prefer one gate over another. In this case, we prefer the NAND gates. And the other difference that you'll see is there is a clock, but there's only one input. There's no more a set or a reset. It's just one single D over here. So if we look at that one, that's this. There's only one D because if you look at the top here, this one, you'll see that it's just whatever you put in. And then down the bottom, there's a NOT gate that just flips whatever you gave it. Does that kind of make sense? So you're getting both inputs in some sense. You just don't have to put them both in. So if I turn this one on, again, nothing happens because the clock is not letting it through. Turn the clock on. If it's a 0, my answer here is Q0. That's the answer. If I turn a 1 on, the answer is a 1. If I turn the clock off, does it stay at a 1? Yep. When I turn the clock on again and I make it a 0, it becomes a 0. So it's remembering the value that I last gave it, and I only need one input. So that's an improvement, right? Okay. So that's the data latch, and we've just seen a number of different variations on basically the same idea. How do we remember stuff inside the computer? We can build different kinds of circuitry. They're very simple or basic in some sense what we've seen. The symbol that you'll see for the D latch is the little square with a D and a Q on the bottom right. Okay, you might see those in some circuit diagrams. In particular, when you want to have multiple bits like memory, you want to glue them together somehow. So we might glue some of these latches together. So if you only addressed one bit at a time, it would take a long time to access everything. So we tend to access things in groups. What's the basic unit in computing that we use? How many bits do we work with at a time? Typically groups of 8. It might be an 8-bit computer, a 16-bit computer, a 32-bit computer, a 64-bit computer. Yeah? So at the moment, we're at the 64-bit sort of range, but the older machines had less bits. And typically, they're groups of 8. So those groups are described as words, but every machine might have a different idea about what a word length is. Your 64-bit phone might be very different about how many bits it thinks as, say, a Commodore 64, for example, right? They have different ideas about what a word means. An 8-bit word is called a byte. We're probably familiar with that. A 4-bit word is called a nibble. It's a cute name. Don't really use that very often. 4 bits is also how many bits a hexadecimal digit has. Right? It's half a byte. And there are no special names for other size words. What we're looking at is building something called a register, and we can glue these data latches together, like those 4 down the bottom there. And if we glue 4 of them together, we have a 4-bit register, or 4 chunks of memory, 4 1-bit chunks. And we call that a register. Typically, we work in 8 bits, so on the right you have a simplification of that diagram, which is an 8-bit register. If we have these registers, which have multiple bits, we have to move the bits around. The bits have to go from one place to another place, one box in memory to another box, and we can connect those boxes together with lines or some way to get that information between the two parts. With registers, we have multiple input and output lines because there are multiple bits. And down the bottom, you'll see that there are 2 models that we can work with, point-to-point and multi-point buses. On the left, you'll see a point-to-point bus. Every bit in your register A has a line that goes to another bit in register B. So every bit is directly connected to a neighbor bit in register B. On the right, you'll see that there's actually a shared bus, and that model there, register A, register B, and the ALU, you can imagine that those are houses. They have driveways going to a shared road, and a car comes out and they have to share the road. It's a different model than if you had your own private road to every other house. Does that also make sense? Okay, so you can share a bus or you can have your own personal point-to-point bus. Moving on to how we actually view memory. Typically we view memory like that grid that's on the page at the moment. Right? So every line has an address. Those addresses start at 0 and they count up to whatever the limit is for this machine. This is a very small machine. It has 0 to 5, so 6 addresses. Not a very useful machine. Good enough for the example. So we can use an array or a sequence of these registers in series to create this memory bank. It's just basically a box, right, with all these memory locations. And we group them in lots of 8. And we give each lot of 8 its own address. So an 8-bit machine would use a bank of 8-bit registers and access 8-bit words from memory at a time. So 64-bit word would access 64 bits at a time, right? So you can do more things in one cycle or one iteration. If you look at this diagram, I think I'll be able to draw this one a little bit more clearly here. So I went through a number of examples here with Logisim. If I'm fetching a word at address 3, where's address 3? Here. A word is 8 bits in this case, so it's all of these 8 bits. So I would get 011001000, and that would be the number 100 in base 10 if I was going to convert it. If I was fetching the word at address 5, what would I get? 1001100. You get all 8 bits in one step. For a 64-bit machine, how many bits would you get in one step? 64. Okay. So when you're working with memory, how do you move stuff backwards and forwards? So the next lecture, we're going to look at the processor. Right? We're going to look at how the processor works. So we're going to need some of this stuff. The key idea, though, is you've got a memory bank. So you've got all these rows that are numbered with addresses, and each row has 8 bits in it. If I want to access a particular part of the memory, what I need to do is I need to tell it, what am I doing? Am I reading or am I writing? Those are different operations. I need to choose one. So let's say I'm going to read something. If I'm reading something from memory, I need to know where, which row, which address. I have something called the MAR, the memory address register, which has a number in it, and that number is the memory address that I'm looking at. What memory address is this? 0011. 3. Great. I'm reading, so what I'm going to do is I'm going to look at memory address 3, and that happens to be 011000100. Where am I going to put that? I'm reading it. I want to store it somewhere. I have a temporary storage space called the MBR, and I'm going to take that value and put it in here and overwrite whatever was there. And now I can use this inside my CPU to do some work with it. So I can tell it what I'm doing. I'm reading, and I'm reading from a particular location, and I'm storing that value somewhere in my memory. Okay. What about if I was going to write? Say this one. Well, same question. Where am I writing? In this case, where am I writing? 3. And imagine that this was a different number. Let's say it's 11110111. I'm taking what's in my MBR, my temporary storage space, and I'm writing it into memory location 3. 11110111. So I use this temporary storage box to keep track of information for me over a short period of time. I read into it, or I write from it. And my CPU is over here able to work with that information, process it in some way if I need to. Okay, we'll look at more detail with the processor later on. So in summary for this section, we had a look at the arithmetic logic unit, multiplication division, multiplying by 2 first of all, and then arbitrary multiplication division, shifting, sequential logic, data latches, and basically how we make memory, how we make a very simple memory. The next section will look at processors, and that's the end of this section.